All right, the last thing we're going to talk about today is identifying three states of matter and describing their properties. I think this is the last thing we're going to talk about. So there are solids, liquids, and gases. And before we go on to that, let's take a look at an example here. Notice that we've got all of these. What are we looking at? We're looking at neon. So these are atoms. And notice that they're packed really tightly together. So what do we have? Do we have a solid, liquid, or a gas? What do you think? Yeah, we've got a solid.
Solid.
But wait. Solids are moving like this. The individual particles in a solid, they're actually moving all the time. Is that true?
No, that's gas.
Oxygen.
No, it is true. So every solid, even the desk or the table that you're sitting at, all of the particles are actually vibrating in space. It's just that the vibration is so small that we are unable to perceive it. So notice here, this is at 14 Kelvin, so it's really, really cold. And if I warm these atoms of neon up, notice that they start to move around. What do we have here? Is this a liquid or a gas?
Gas.
Liquid. It's liquid.
Liquid.
So the ones down here in the bottom.
Oh, because it vibrates. Okay. Okay.
And in every liquid, there's almost that can break free from the liquid and become a gas, right? So here we go. Let's see specifically a liquid. Now, notice that some of these atoms are breaking free every once in a while. Because they're bouncing into each other, and some get enough energy to break free. Now let's heat it up a little bit more.
That's gas.
Yeah. So notice that the gas, they're all flying all around. They're all over the place. They're bouncing around. They have way more energy than everything else. You see that? And if we were to lower the heat, if we take away some of that energy, notice what will happen to this gas. Now remember what the temperature was before when neon was a solid. How far do we have to get down in order for neon to become a solid again?
14,
you guys remember?
14 Kelvin.
Right? So you notice, you see how now we're back at a solid. Okay, let's take a look at, let's do water. So water solid. Hey, wait, why isn't it all packed up all tight like the neon was? Well, actually, because water is a very special substance, and it actually, the density of water when it's frozen is lower than water when it is liquid. You guys know that because ice floats, right? So that must mean that the density of frozen water or solid water is going to be less than liquid water. Now let's see a liquid. Did you guys notice how the arrangement got closer in a liquid than it was in a solid? So let's go back again. So this shows you that the density is a lot less. Why? Because there are fewer particles packed into one space, right? That's what density is. It's mass per unit volume. So notice that there are fewer water molecules packed into the same amount of space, whereas in a liquid, they are packed a lot tighter. And it has to do with their interactions with each other. And I don't know if you guys are noticing, but water molecules are rearranging themselves so that the hydrogens and the oxygens are attracted to each other. Now let's look at what happens when this becomes a gas. Notice the temperature. It's over 100 degrees Celsius. Kelvins, you just add 273. And notice how fast these molecules are moving around. Okay, so let's go back to our PowerPoint. And now let's go over our properties of where am I? Of solids, liquids, and gases. Okay. So there are 3 states. We won't talk about plasma, so there's another state called plasma, but we'll keep it simple here. There's solids, liquids, and gases. And when the state changes, we have a conversion of a substance from one state to another. So let's give you another visual of these states of matter. So do you guys remember, how many of you, when you used to go to elementary school, you either had to line up like outside on the playground or in the gym? You had to line up in your classes. Anybody remember that? Anybody? Yes, no? And everybody had to line up like this, and everybody was all nice and neat in their line and have their book bags on. Let's imagine now the monitors came around and gave everybody Frosted Flakes. And then once they get the sugar in them, they started to I'm sorry. They give sugar, and kids start pulling on each other's book bag, and they start poking each other in the back, and they start tapping on each other. And then soon everyone's just running all around the gym or moving all around like bad people. So everybody in line, everyone's standing in line, nice and neat. That would represent a what? What would that represent?
Solid.
Yes, solids. When everyone starts poking each other and stepping out of line and starts doing, tapping each other and that sort of thing, what would that represent? Liquids. Yes. And what about now when everyone's running all around the gym or all around the playground? That represents a gas. So what was the difference between the solid, the liquid, and the gas? And just like in the example that I showed you guys a little while ago, what was the difference between them? What was the difference between all of those?
They're more free to move around because they're less compacted.
But why? Why are they more free to move around? What was it? Energy, Andrew.
Yes.
And how packed they were. Well, the closeness of the molecules or particles get closer together when there's little energy. The more energy, they start vibrating more rapidly, and then they start bumping into each other. The more they start bumping into each other, they start breaking away from a liquid and then become a gas. So the conversion of a solid to a liquid has to do with the amount of energy. So melting is going from a solid to a liquid. Freezing is going from a liquid to a solid, right? Going from a liquid to a gas is called evaporation, but going from a gas to a liquid is called condensation. And there's another state change that is where a substance can go from a solid straight to a gas, and that is called sublimation. and deposition is the opposite. Now, sublimation. Anybody know of any substance that can do sublimation? Anybody know? Anybody ever been to a party and they had like smoking Kool-Aid or smoking punch? Anybody? Yes. So that is, yes, CO2. So carbon dioxide is dry ice, and dry ice sublimates. It skips the liquid phase altogether at room temperature, and it becomes a gas. Liquid nitrogen does not sublimate because it's a liquid, and it goes from a liquid to a gas. Okay, so sublimation is directly from a solid to a gas. So liquid nitrogen is evaporation. It's just that doesn't mean that it can't become a liquid at a lower temperature. So the temperature has to be a lot lower than room temperature in order for it to become a liquid. So it has to be like really, really cold. So an example of deposition, have you ever gone outside in like when it starts to get cold out and you go outside and you see that there is frost on people's cars and frost on your windows? That is an example of deposition. So what that is that there is water vapor in the air, right? And your windows or the cars are so cold that when the water touches the window, it immediately becomes a solid. It's also what you see in the morning on like the grass and that sort of thing, if you live where there's grass. All right, so what causes the state change is either the input or the removal of energy. So adding energy, we will go forward, and those are the ones that are written in red. If we're removing energy, we're going in reverse, and those are the ones that are written in blue. Right, so what are the properties of matter? The properties of these three different types. So gases, the particles are widely separated and there is no definite shape or volume. Whereas liquid, the particles are closer together. There's a definite volume but no definite shape. So let's say you have a whole bottle of water and you knock that water over. It now spills on the floor. You still had a whole bottle of water with a definite volume, but the shape now is just a pool on the floor, right? So it has no definite shape. It takes the shape of its container. Solids are the particles are very close together. There's a definite shape and a definite volume. And although my cup does not appear to be vibrating, the particles do not appear to be vibrating, they definitely are. So the only temperature at which there's almost no movement is at 0 kelvins, or what we call absolute zero. So that's the coldest that you can get. And at that temperature, particles don't move. For the most part, they don't move at all. Okay. So reversing is energy removed. Yes, so removing energy is going in the reverse. So let's go back to that slide right quick. So freezing, condensation, deposition are going from a liquid to a solid, a gas to a liquid, and a gas to a solid. All right, that would be the removal of energy. In the example, in the little example that I showed you, notice that when I turned up the temperature, it was like a flame underneath the substances. And then when I decreased the temperature, it was like some ice particles underneath the substance. So that's how we remove energy. All right. Many substances can exist in all three phases, and they participate in changes of state. So like water can be a gas, a liquid, or solid, right? At room temperature. Carbon dioxide at room temperature can only go from a solid to a gas. So it depends on what temperature you're at. And notice that if you have a glass of ice water, although the ice and the water are both present at the same time, the ice quickly melts and you no longer have ice. So like sometimes I go and I walk to Panera and I order an iced coffee, and I walk home. So I walk to Panera and I walk home. By the time I'm finishing up my iced coffee, there's no more ice. First of all, because I stirred the daylights out of it to dissolve my sugar in the coffee, which moving things around creates energy. So that helps my ice to melt. And then the temperature outside also increases the temperature of my ice, and my ice melts by the time I'm finished drinking my iced coffee. Now, can you guys see the little particles? Can you see the little spots inside my water bottle?
Yes.
Like it's empty. There are some pools of water, but the little teeny tiny speckles, dots, that's the water vapor that's condensed on the sides of the bottle. So inside this bottle, what I can't see is that there's water vapor. And only when it comes in contact with the plastic does it actually condense on the side, and now it looks like a liquid. So even at room temperature, water can be a gas. So here we go. Here are some models of solids, liquids, and gases. And here we have a solid. Notice that the particles are all tightly packed together as close as they possibly can, except for water, because it's special. And in liquid, notice that the particles are tight together, but they're randomly spaced. They don't have like a really uniform packing. And these shadows behind these particles represent the fact that they're moving, right? And notice here in this example of a liquid that we've got one of these particles that broke free from the liquid. And sometimes so sublimation is what happens to most of the snow that we get. So most of the snow that we get doesn't melt, it sublimates. So if the sun is shining really brightly on a pile of snow, a lot of the water will just sublimate, and you don't see a puddle of water. You know, sometimes you look outside, it's like, where did the snow go? There's no pool of water around. And sublimation is what has occurred to that snow. Let's see, is there any chat going on? Okay, cool. So if you open this PowerPoint and you click on this link, you will go to that simulation that I showed you a little while ago, this one here. Let me go back. Can I go back? Let's see. So let's take a look at phase changes. So if oh, that's adding in more. So what's this? If I compress the pressure, so let's start with neon as a, hold on, let's go back up. So not only is temperature, come on, reset. Not only is temperature a way to change things from a solid, from a a liquid to a solid, but something else that can change things is pressure. So notice as I'm warming up this container, this is a closed container, right? It's completely closed. And as I increase the temperature, I increase the pressure of these gas molecules on the wall, right? Now, if I increase the pressure increase the pressure, let's keep going. Oh my gosh, what happened to our system here? The pressure got so high that the top flew off.
Go.
Yeah, the top exploded it, right? So the properties of gases is that if the pressure gets too high, anybody ever had like you ever look, yes, the gas won the battle. Poor finger. The gas won the battle. You ever notice on like spray cans that it says do not incinerate?
Combustible.
Yeah, it says do not incinerate, and it says contents under pressure, right?
Yeah.
So what that means is that gas is in a tank, right? And it's in a closed system, just like we had here, right? And if you put that in the incinerator, the pressure essentially gets so high because notice that as the pressure increased, the temperature was going up as well. Did you guys notice that? Come on, finger. Notice that the temperature is going up.
Yes.
So the temperature goes up so high that that can would explode in the incinerator. All right. So not only does temperature affect whether a substance is a solid, liquid, or a gas, but also pressure, right? So if we compress things to a certain degree, then we would end up with a liquid. So you ever notice that in the oxygen tank, like those oxygen tanks have, so if the pressure increases, then will the energy decrease? If the pressure increases, no, actually, the energy doesn't decrease, it just forces them to go together because notice the temperature goes up. So if the temperature is going up, then the energy is not decreasing, right? So those spray cans, they get cold when they're used. That's mainly because you're releasing some of the gas and the pressure. Yeah, the pressure drops when the gas exits, so the temperature goes down. That's why. So notice that increase of pressure increased the temperature. So when I decrease the pressure, I decrease the temperature. So when you turn a can of CO2 upside down, it's colder, but why? I've never experienced a can of CO2. I'm not sure what that is. But back to my other example was that oxygen, probably more than all the oxygen that is in your, all the oxygen that is in the room that you're in right now could be put into an oxygen tank, and you probably have more room to go in, right? So as you increase the pressure on that oxygen, it actually becomes a liquid. So inside of an oxygen tank, it's not oxygen gas, it's oxygen liquid, and it's because the pressure is so high. All right, back to our PowerPoint.